Hello everybody. In today's video, we'll start discussing the chapter inductors. So till now we have discussed two other basic components, that is resistors and capacitors, and the other most common type of or the most common basic electronic component is inductor. So from this session we'll try to learn what is all about inductors. And for today's video, the learning objectives will be inductors and what are the symbols of inductor. And here we find two different types of inductance for any inductor. One is self-inductance, the other one is mutual inductance. For this video, we'll just learn what is meant by self-inductance and how we write the self-inductance and what are the factors that affect self-inductance will be discussed in this video. Okay, so let's start discussing what is about inductor. So an inductor is a passive electrical component and it consists of a coil of wire, and it is designed to take the advantage of the relationship between magnetism and electricity as a result of an electric current passing through the coil. Okay, so here we see a coil of wire in which when current flows through that coil, because of the current flowing, magnetic property can be observed, and that we call it as inductance. Okay, so when we are discussing about electromagnetism, we saw that when an electric current flows through a wire, a magnetic flux is developed around the conductor, right? This effect produces a relationship between the direction of the magnetic flux, which is circulating around the conductor, and the direction of the current that is flowing through the same conductor. Okay, so this results in a relationship between current and magnetic flux direction, and this relationship what we got to know is Fleming's right hand rule, right? So the relationship between the current and magnetic flux is given by Fleming's right hand rule, and this point we have discussed while we are studying electrostatics. Okay, so the same concepts will be applicable here also for the inductors. So there is another important property that is relating to a wound coil that also exists, which is that a secondary voltage is induced into the same coil by the movement of the magnetic flux as it opposes or resists any change in the electric current flowing it. Okay, so coming to the inductor, what we call inductor, this is nothing but a passive component, and it is a most basic form of an inductor is nothing but, here you can see on the screen, this is the most basic form of an inductor. So it looks more like a coil of wire wound around a core. So a simple wire which is wound on a core is called as an inductor. So the most of the coils, the current will be flowing through the coil and produces a magnetic flux. So the current I will produce a magnetic flux N.P.V in the coil or else around the coil, and around it that is proportional to the flow of electric current. So the amount of flux that is produced in the coil is directly proportional to the current that is flowing in the coil. Okay, so it is very simple that when current is flowing, magnetic flux will be developed around the coil, and that will be proportional to the amount of current that is flowing, right? So here an inductor is also called as a choke. So choke is also a passive type of electrical component consisting of a coil of wire, and it takes advantage of uh, advantage of this relationship by inducing a magnetic flux in itself or within its core as a result of the current flowing through the wire coil. Okay, so inductors and chokes are one and the same, so they will work on the same property, that is nothing but development of magnetic flux. So inductors are generally formed with a tightly wrapped wire around a central core, which can be either a straight cylindrical rod or a continuous loop or a ring to concentrate their magnetic flux. So I have shown you a circular wound inductor on the screen, but not all the times inductors won't be of this type. Inductors can be of any type, like it may be a rod type, or it may be some loop type, or it may be circular in shape. But the thing is that for an inductor there will be a core. On the core, coil will be wound, some conducting wire will be taken and that will be wound, and that forms an inductor. And this, here when you come here you can see the symbol of a inductor. So here you can see this is pretty much similar to that of a resistor, right? But for resistor we see some zigzag lines between the two terminals, but here we see a wounded thing of wiring here. So when we see zigzag line, that is resistor. The wounding kind of fashion we call it as inductor. Okay, so the schematics symbol for the inductor is that of a coil of wire. So therefore a coil of wire can also be called as an inductor. So inductors are usually categorized according to the type of the inner core that are wound around. So just now I was telling you that inductor is nothing but a wire which is wound on a core. Sometimes they may be or they may not be core, but the coil will be present. So in a simple construction, that is, if there is no core, based upon the core, the inductors can be of some basic four types can be there. Like when we have no core, we call it as air core. Air core inductor we call. For example, or it is also called as hollow core or free air. Otherwise, we can also have iron core. So you can see it in the symbol. This inductor will have two straight lines attached to it. This is indicating that the inductor is an iron core. This is a symbol for iron core inductor. And the third one is ferrite core. That is, the coil can be wound on even on the ferrite material. So if we wound a coil on a ferrite material, then we call it as ferrite core inductor. And like resistors and capacitors, we have inductors in variable category also. So for the variable category we use an arrow, right? So we simply take a inductor, and onto it we give it an arrow, then we can say that this is a variable core inductor. So these are the basic symbols of inductors: air core, iron core, ferrite core and variable core. So what I am trying to say is that inductors are generally categorized according to the type of the inner core. Basic classification this is, right? So based on the inner core, they can be either air core, iron core or soft ferrite core, with the different core types being distinguished by adding continuous or dotted lines next to the wire core, which I have shown you just now. Okay. So in this diagram also you can see a straight rod on which a coil is wound, right? So this straight rod is nothing but the core, and on the core we have wound some wire, and now the entire setup, that is coil and this core, is now called as an inductor. If we take this with iron material, if the core is iron, then we call it as iron core inductor. So as you can see, here the current I is flowing in the coil to the applied voltage V, and these are nothing but the number of turns will be indicated by letter N, and the length of the core is given as L, whereas area of cross section of the core material is taken as A. So when you remember these points, we can easily derive an expression for the inductance. Okay, so the current I that flows through the inductor produces a magnetic flux that is proportional to it. But unlike a capacitor, which opposes a change of voltage across the plates, an inductor opposes the rate of change of current that is flowing through it. There is a difference between capacitor operation and inductor operation. Capacitor opposes the change of the voltage across its plates, whereas inductor opposes the rate of change. Okay, there is a slight variation. Capacitor opposes the change of voltage, whereas inductor opposes the rate of change of current that is flowing through it due to the buildup of the self-induced energy within its magnetic field. Okay, so in other words, we can say that inductor resists or opposes the changes of the current but will easily pass a steady DC current. Got the point? So that is, a DC current will be easily flowing into the inductor, whereas inductor will resist or opposes any change of the current that is applied to it. So this ability of an inductor to resist changes in the current, and which also relates current I with its magnetic flux linkage N.P.V as a constant of proportionality, is called as inductance. Okay, so I repeat. Here you can see the ability of an inductor to resist the changes in the current, and which also relates current with its I with its magnetic flux linkage as a constant of proportionality, is called as inductance. And inductance is generally represented by letter L. And coming to the units of inductance, Henry H, indicated by letter H. Henry is a unit of inductance, and it is named after the scientist Joseph Henry. Okay, so this is inductance. But here, in capacitor, we have seen farad. Farad is basically a very large unit. That is why we use microfarads, nanofarads. Likewise, here also, Henry is a relatively large unit of inductance. That is why for smaller inductors, subunits of Henrys are used to denote its value, like microhenry, nanohenry, millihenry units will be used for inductors, similar to that of capacitors. And coming to the actual definition of inductance, how we define inductance is, here you can see the inductors, or we can simply call it as coil. Okay, so remember, inductors, or otherwise called as coils, are very common in electrical circuits and are many factors which determine the inductance of a coil, such as the shape of the coil, the number of turns of the insulated wire, the number of layers of the wire, the spacing between the turns, the permeability of the core material, the size or the cross sectional area of the core, etc., are some of the points on which the inductance will be dependent. Okay, so all these factors like the size, shape, number of turns, spacing between them, and the permeability of the core material, all together will determine the inductance of the inductor. So an inductor will generally have a central core area. I'll show it in the diagram. I'll show you the diagram. So it will have an inductor has a central core area which is indicated as A with a constant number of turns of wire per unit length. So here you can see the number of turns as N for unit length of L. So for the given length, the number of turns will be decided. So if a coil of N turns is linked by an amount of magnetic flux pi, then the coil has flux linkages of N pi. That is, N is nothing but the number of turns. And any current I that flows through the coil will produce an induced magnetic flux in the opposite direction to the flow of current. Got the point? So the induced magnetic flux is in the opposite direction of the flow of the current. Then according to the Faraday's law, any change in this magnetic flux linkages will produce a self-induced voltage in the coil, and it will be given by an expression. Here I'll show you the expression. So according to the Faraday's law, any change in the magnetic flux linkage produces a self-induced voltage, and that voltage VL is given as N into d pi by dt, and that can be written as mu N square A by L into d pi by dt, where N is the number of turns here, A is the area of cross section and the units are meter square, pi is the flux in Webers, mu is the permeability of the core material, L is the length of the coil, we'll indicate it in meters, and d pi by dt is the rate of change of current, and it will be indicated by indicated with the units amperes per second. Right? So this is the amount of voltage that is developed in the inductor when a current I is flowing. So a time varying magnetic field induces a voltage that is proportional to the rate of change of current, producing it with a positive value indicating an increase in EMF and a negative value indicating a decrease in the EMF. Got the point? So if the expression is positive, then it shows an increase in the EMF, and if the expression is in the negative terms, we can say that it is indicating a decrease in the EMF. The equation relating this self-induced voltage, current and inductance can be found by substituting mu N square A by L with the letter L indicating the constant of proportionality. So in this expression, mu N square A by L can be substituted by simple letter L, constant letter L. So that constant L is nothing but the inductance of the coil. So then when we substitute L here in this place, then the expression will become VL is equal to minus L d pi by dt volts. It's very simple, right? So the voltage that is developed because of the rate of change of current in the coil, we can write it as VL is equal to minus L d pi by dt. right? So from this expression we got to know there is a relationship between L, V and I, right? So now we'll try to define what is meant by inductance. Now we'll try to define what is meant by inductance. So inductance is nothing but a coil will have an inductance value of 1 Henry. Okay, a coil will have inductance of 1 Henry when an EMF of 1 volt is induced in the coil, where the current flowing through the said coil changes at a rate of 1 ampere per second. Okay, for 1 Henry 1 volt of EMF is induced and it is causing 1 ampere per second rate of change of current. In other words, a coil has an inductance L of 1 Henry when a current flowing through the coil changes at a rate of 1 ampere per second. This change induces a voltage of 1 volt in it. Thus, we can represent the rate of change of current through a wound coil per unit time as d pi by dt, amperes per second, where di is the change in the current in amperes and dt is the time taken for the current to change in second. Then the voltage that is induced in the coil with an inductance of L henries as a result of this change in the current can be expressed by this expression, that is VL is equal to minus L d pi by dt volts. So here we are seeing a negative sign here in this expression. The voltage expression we find a negative sign, and this negative sign indicates that the voltage induced opposes the change in the current through the coil per unit time. So as there is an opposition, the voltage induced will oppose the change in the current. That is why we indicate the voltage VL, the voltage developed in the inductor, with a negative sign. So how we write L is from the same expression. If we take L to the left side and VL to the right side, we can simply write it as L is equal to VL by d pi by dt. This is nothing but 1 Henry. That is, if VL is equal to 1 volt, di by dt is equal to 1 amperes per second, then what we get is nothing but 1 Henry. So 1 Henry is nothing but, when we give 1 volt and the rate of change of current is 1 ampere, the value what we get is nothing but 1 Henry. Here L is nothing but the inductance in henries, VL is the voltage across the coil, and di by dt is the rate of change of current in ampere per second. Okay, actually inductance is actually the measure of an inductor's resistance. Inductance is nothing but, it is basically a measure of inductor's resistance to the change of the current flowing through the circuit, and larger it is, its value is henries. The lower will be the rate of change of current. Okay, so simply you can remember that inductance is nothing but how much resistance an inductor is offering to the rate of change of current in it is called as inductance. And here another point to be noted is that inductors are the devices which can store energy in the form of magnetic field. So in contrast to capacitors which store electrical energy, inductors are the devices which store magnetic energy in them. So inductors are generally made up of individual loop of wires combined to produce a coil, and if the number of loops within the coil are increased, then for the same amount of current through the coil, magnetic flux will also increase. Got the point? If the number of loops are increased, the same amount of current flowing through the coil, the magnetic flux will also increase. So, by increasing the number of loops or turns within the coil, increases the coil inductance. Okay, so just by increasing the number of turns, inductance can be increased. So the relationship between inductance L, number of turns N, and the flux current can be given simply as L is, I'll show it in the next diagram, that is self inductance. L is equal to, we can write it as based upon number of turns, flux and current. We can write self inductance as L is equal to N pi by I. So here, before going into this point, I have to mention you one point, that is nothing but types of inductance. Okay, till now it is clear, no? So inductance is nothing but the property that is exhibited by inductors. Inductance is nothing but the opposition that is offered by the inductor to the rate of change of current that is flowing in the coil is nothing but inductance. Okay, so inductors generally exhibit two kinds of inductance. First one is self inductance and the other one is mutual inductance. Here we are talking about coil and magnetic flux, right? And that magnetic flux will be developed because of the current that is flowing in the coil, right? So the coils sometimes may be connected more in number in any circuit. So if what is the difference between self and mutual inductance is, if the magnetic flux that is developed in a coil because of the current that is flowing in the coil itself is called as self inductance. Whereas when we talk about mutual inductance is nothing but because of the voltage or because of the voltage that we apply to one coil. Okay, the voltage will be applied to one coil, and because of the current that is flowing in the one coil, the voltage will be induced in the nearby coil. Okay, same magnetic property. Okay, because of the current that is flowing in one coil, voltage will be induced in the nearby coil. So this property we call it as mutual inductance. Okay, so in today's session we'll discuss simply what is meant by self inductance, and in the next coming video we'll discuss what is meant by mutual inductance. But the point is, self inductance is nothing but when a EMF is induced in the same circuit in which the current is changing, and this effect is called as self inductance. In general, sometimes we consider this self inductance as a special case of mutual inductance because it is produced within a single isolated circuit. We generally call self inductance, or simply we can call it as inductance also. And for the measurement of inductance, the self inductance has a unit called as Henry, but it can also be represented by units Weber per ampere. 1 Weber per ampere can also be used as a unit for inductance. It is sometimes commonly called as, that is self-inductance is sometimes called as back EMF also, as its polarity is in the opposite direction of the applied voltage. Okay. So here I have given you an expression relating L, N, pi and I. So the point to be noted regarding this expression is that this equation applies only to the linear magnetic materials. Now, knowing what is meant by L, we'll try to go in detail on what factors this L will be dependent. Okay. So here we can see that for a self-inductance coil, or to be more precise, the coefficient of self-inductance can also depends on the characteristics of its construction, like what I have said, like N, L, mu, B, and these are all the factors, like for example size, length, number of turns, etc. It is therefore possible to have inductors with very high coefficients of self-inductance by using cores of high permeability and large number of coil turns. Okay. So then for a coil, the magnetic flux that is produced in its inner core will be equal to pi is equal to B into A. Okay. The magnetic flux in the core can be written as pi is equal to B into A. We know that pi is nothing but the magnetic flux, B is equal to flux density, A is the area. Okay. So if the inner core of a long solenoid coil with n number of turns per meter per length is hollow, or if it is air core, then the magnetic induction within the core can be written with this expression, that is B is equal to, that is the value B can be written as mu naught into H. Okay, where H can be written as N into I by L. Okay, when we substitute this H value here, we can write it as mu naught into N into I divided by L. Then by substituting this expression in the first expression, what we have written here, okay, L is equal to N pi by I is the known expression for us. If we substitute the value of pi here, we know that pi is equal to B into A, right? So substitute that one here. Then we can write it as N into, instead of pi, we write it as B into A. And here B can be written as mu naught into N into I divided by L. So that is what I have substituted here. So what I can write is L is equal to N into mu naught N into I divided by L into I into A. So when you see here, there are some terms that can be cancelled out, that is here I and I can be cancelled here. Okay, so then we can after cancelling and grouping all the terms together, the final expression for coefficient of self-inductance of an air-cored coil can be simply written as L is equal to mu naught into N square into A divided by L. Okay, so self-inductance L can be written as, by taking all the parameters into consideration, that is like its size, turns, flux density, area, length and all. If we take all those parameters into consideration, we can write the self-inductance L as mu naught into N square A by L, where we know that L is nothing but the inductance or self-inductance in henries. Mu naught is a permeability of the free space. It has a constant value 4 pi into 10 power minus 7. So this is a constant value that you can remember, where N is a number of turns, A is the inner core area, that is in meter square, L is the length of the coil in meters. Okay, so this is the expression that what we give for self inductance of the coil, or we can say that these are the factors that influence the self inductance of the coil. Based on the expression, if we change N, L changes. If we change A, L changes. If we change L, that is length, the total self inductance will change. Okay, so this is on which these are the parameters on which self inductance will be dependent. So as the inductance of the coil is due to the magnetic flux around it, the stronger the magnetic flux for a given value of current, the greater will be inductance. This is very simple, right? So if the magnetic field is strong, then the inductance will be greater. So as a coil of many number of turns with higher inductance value than one for only few turns, and therefore the expression will give inductance L as being proportional to the number of turns squared as N square. Okay, so in this expression we observe it as N square, right? So the more the number of turns, the higher will be the inductance. Okay, got the point? So if you want to increase the inductance or self inductance, you just increase the number of turns that you wound on your core. So the more number of turns will give you more inductance. Okay, got the point? So these are the points that we can discuss regarding self inductance. So in addition to this, we can also talk like some other points, like, so as well as increasing the number of coil turns, we can also increase the inductance by increasing the coil diameter or by making the core longer. In both the cases, either by increasing the coil diameter or by changing or by making the core longer, in both the cases more wire is required to construct the coil, and therefore more lines of force exist to produce more magnetic flux, or more EMF will be produced, right? So if you take a thick wire or if you increase the length of the wire, more EMF will be induced. So thereby self inductance will be induced. So the inductance of the coil can be still further increased if the coil is wound on a ferromagnetic core. So this is one which is made up of soft iron material that one wound on a non-ferromagnetic or hollow air core. Okay, so the inductance can be increased if we use ferromagnetic core instead of hollow air core materials, then inductance will also increase. So if the inner layer of the core is made up of some ferromagnetic materials such as soft iron, cobalt or nickel, the inductance of the coil would greatly increase because of the same amount of current flowing through the magnetic flux generated would be much stronger. So this is because the material concentrates the line of force more strongly through the softer ferromagnetic core material. That is what we have discussed in when we talk about electromagnetism, right? So that is why because of the soft iron materials or cobalt or nickel, we can see an increase in the inductance of the coil. For example, if the core material has a relative permeability of 1000 times greater than free space, so 1000 into mu naught, such as soft iron or steel, then the inductance of the coil would be 1000 times greater. So we can say that the inductance of the coil increases proportionally as the permeability of the core increases. Okay, so what I am trying to say here is that if we increase the permeability, inductance increases. If we increase the area of the area of cross section of the coil, or if the length of the coil is increased, inductance will increase. And as well as if we use ferromagnetic material as core, we can increase the inductance. So these are all the points what can influence the inductance of a inductor. So by varying these points within the given inductor, the inductance value can be changed. So from this you can understand that the inductors with the same size may not have the same number of turns, or may not have the same wire which has the same cross sectional area, right? So if all these parameters match each other when we take two different inductors, then only the inductors will show same inductance value. Otherwise, if any of these parameters vary, two inductors will show two different values. So within an inductor, we can increase or decrease the inductance value just by changing the physical parameters of the inductors. Okay, so with this we'll conclude the session for today. So by knowing these points, like we have discussed what is meant by inductor, what is meant by inductance, and on what factors inductance will be dependent, or what is the voltage expression that we give for inductance is it has been discussed. The symbols for inductors have been discussed, and later on we have discussed what are the different types of inductors, and from that what is meant by self inductance is learnt, and what are the factors that can influence the self inductance, and what are the ways we can change the self inductance has been discussed in today's session. And in the next coming video we'll discuss what is meant by mutual inductance, and as well as what is meant by coefficient of coupling will also be discussed in the next coming video. Okay, thank you.